Good morning. Let us continue our discussion about valence bond theory. Let us see what is a bonding or nature of the bonding in ammonia molecule. Here you have to start with nitrogen. So, what is the electronic configuration of nitrogen is 1s2, 2s2, 2p, 3. So, you can write 2s level, this is 2s level containing 2 electrons, and then there is a p orbital, 2p orbital, and then it has some 1 electrons here and here. Now, it has to hybridize, so that Sp3 hybridization is obtained. Here, so this orbital to form 3 covalent bonds. In addition, there is a lone pairs. So, all of them should be accommodated in the bonding. So, you need to have Sp3 hybridization. How does it work? So, here you have 2s orbital and 2p orbital. 2s orbital is completely filled, however, 2p orbital are singly occupied. They can hybridize. So, hybridization, hybridize and can give 4 equivalent hybridized orbitals of this type. This is Sp3 hybridized hybrid orbital. You can notice that which are the orbitals hybridize. It is not that if you take a carbon CH4, you have all, okay, there is a promotion of electron from 2s orbital to 2p orbital. That is for carbon you have a 2s orbital and then you have a 2p orbitals. So, here there is a, it is a electronic configuration of the carbon, and then one of the electron of the 2s orbital should go to this 2p orbital, and then then it has to sp hybridization going on. So, the hybridization occurs there between the singly occupied s and p orbitals. On the other hand, here the hybridization occurs between 2s orbital, which is completely filled, and 2p orbital, which are singly occupied. So, it is not necessary that for hybridization to occur that all the orbitals should be singly occupied. Okay, hybridization can take place between orbitals of this type. So, you have Sp3 hybridized orbital in which one of the Sp3 hybridized orbitals is occupied by 2 electrons. So, that means it is completely filled, and then you have remaining 3 Sp3 hybridized orbitals available for forming bond. So, you can draw the structure in this way. So, you have a nitrogen, and then you have a one lobe, another lobe, another lobe, and another lobe. Because it is Sp3 hybridized, the geometry is tetrahedral. So, you have to draw the hybridized orbital in a tetrahedral arrangement. So, that these are the lobes of the Sp3 hybridized orbital, which are pointed towards the corners of a tetrahedron. So, this is available for forming bond. So, you have then hydrogen atom, hydrogen 1s orbital, and then another hydrogen 1s orbital, and then you have hydrogen 1s orbital. Okay. So, they form 3. So, 3 bonds, and then the remaining lone pair okay, you have has to be put here. Then this is equal to this structure. I am redrawing that structure here. That is all. So, as you can see here, the overlap of the atomic orbitals between the Sp3 hybridized orbital of nitrogen with hydrogen 1s orbital. There are like that 3 like that. So, now let us see. So, the structure of the or the molecular geometry of the ammonia is not a tetrahedral, it is a trigonal bipyramidal. So, trigonal pyramidal. Okay. Now, let us see another molecule, water, H2O. Okay. For the central atom is okay, oxygen. So, if you look at the electronic configuration of oxygen, 1s2, 2s2, 2p4. So, okay, energy level is 2s orbital containing 2 electron, and then you have p orbital containing 4 electrons, like this. Now, they can undergo, so there is no need of promotion of electrons, because there are already 2 orbitals containing 1 electron each. So, what will happen is then it has to undergo hybridization, hybridize and generating 4 equivalent Sp3 hybridized orbitals, which contains lone pairs in 2 of the orbitals, and 2 orbitals contains 1 electron each. So, it is a Sp3 hybridized orbital of the oxygen atom, hybrid orbital. Now, you can see again that hybridization takes place here. This is 2p orbital, it takes place between 2s orbital, which is completely filled, and 2p orbital, in which one of them, for example, this px orbital is completely filled. So, they hybridize to give a 4 equivalent Sp3 hybridized orbital, in which 2 of them are occupied by 2 electrons, and then you have 2 Sp3 hybridized orbital containing 1 electron each, which is available for forming a covalent bond with hydrogen. So, you have then, because it is Sp3 hybridized orbital, so it is a tetrahedral geometry. You can draw the structure like this. Okay, these are the 4 Sp3 hybridized orbital. Then you have hydrogen. Okay, then that hydrogen can overlap with the Sp3 hybridized orbital, and then so this is a hydrogen 1s orbital, and then you have hydrogen 1s orbital. So, there are 2 covalent sigma bonds or covalent bonds are formed, and these 2 orbital contains lone pair 1 each. So, you have a structure of bent structure, molecule, the geometry of the molecule is bent. So, that way the molecular orbital, sorry, valence bond theory gives explanation for the observed geometry. It is bent because of the overlap of the 2 Sp3 hybridized orbital with 2 hydrogen 1s orbitals in this way. So, because they are adjacent to each other and there is a repulsion between the lone pairs, between these 2 lone pairs, they push these 2 covalent bonds together. As a result, the bond angle, so the angle between this hydrogen and this hydrogen is not 109.5, it is lesser than that, because of the repulsion between the between lone pairs as well as lone pair bonding electron pairs. Now, let us see furthermore about valence bond method of treating bonds in other molecules. For example, ethane, it is you know the structure, this 2 CH3 groups are bonded through carbon, CH3 groups are bonded together, this is ethane. Now, because the carbon is connected to 4 atoms, so the carbon has a Sp3 hybridization, similarly this carbon has Sp3 hybridization. So, then you know that from your knowledge about the CH4, okay, there are 4 Sp3 hybridized orbital on the carbon. So, similarly in this carbon you have 4 Sp3 hybridized orbital, 3 of them are used for forming 3 covalent bonds with 3 hydrogen atom, and then the remaining one is used to form a covalent bond with another carbon atom of this adjacent another carbon atom of this one. So, there is a covalent bond formed between the 2 carbon atoms. So, that can be drawn in this way. Carbon, you have lobes, Sp3 hybridized lobes, and then there is a lobe. Okay. These 3 are used for forming covalent bonds with hydrogens, hydrogen 1s orbital, this is hydrogen 1s orbital, this is hydrogen 1s orbital. The remaining this sp hybridized orbital is used to form a sigma bond with the adjacent carbon atom. So, you have a carbon atom which also has the same sp3 hybridized orbital, and then you have here 3 more sp3 hybridized orbital, and then these are used to form sigma bond or covalent bond with the hydrogen atom. So, this is a sigma bond. So, this is equal to this structure. Like that. So, it is clear now. So, the bonds are formed essentially by overlap of the atomic orbitals between hydrogen 1s orbital and carbon sp3 hybridized orbital, and then there is a sigma bond formed between sp3 hybridized orbital of one carbon with the sp3 hybridized orbital of the another carbon. So, that there is a sigma bond between them. Now, let us see pi bonds. So far we have seen sigma bonds. Let us see pi bonds. What is pi bonds? So, you know that what is sigma bonds. So, sigma bonds can form by overlap of the atomic orbital. Which are the atomic orbitals? S orbital can overlap with another s orbital to give a sigma bond. Okay. So, this is a sigma bond, SS overlap, this is SS overlap. Okay. So, after that this can be written as like that. This is the center of the nucleus. So, this is a internuclear axis, and these are the nuclei of 2 hydrogen atoms, for example. So, you have here everywhere it is positive. So, this is a sigma orbital, a sigma bond. Okay, this is a sigma bond. It is a sigma bond. It is, this bond is cylindrically symmetrical. This sigma bond is cylindrically symmetrical, and then same sigma bond could also form by the overlap of the hydrogen 1s orbital with p orbital or any s orbital. Okay, this is a p orbital. Okay, plus plus, this is plus everywhere. Sign of the wave function should be given. Sorry, this is minus, and then they give like this. This is positive. Okay, this is negative. So, this is again a sigma bond formed between s orbital and p orbital. Similarly, overlap of the p orbital can also give a sigma bond. Of this type. This is a PP overlap. This is SP overlap. Okay. So, this is again a sigma bond is formed by overlap of the p orbital. So, p, okay, we have seen how sigma bonds could form. It could form by the overlap of the 2 s orbital, by the overlap of the s orbital with the p orbital, or 2 p orbitals. Now, you know that if you take a molecule A and B, then for any molecule one has to fix the axis. Okay. Then we can find out the what are the orbitals overlapping, and then the bonding pattern we can find out. So, if you take a axis of this like this. Okay. So, let us see, we have to fix a axis for this molecule. Okay. Let us say this is z axis, this is y axis, this is x axis. Now, if you fix axis for this molecule as the as this axis, if you fix this axis as z axis, then okay, then the orbital, then the atom A should use its px pz orbital to form a sigma bond. So there is a for example, there is a p orbital lying along the z axis, so it is a px orbital. So there is similarly there is a orbital lying along the y axis, this is a px orbital, py orbital, then there is a orbital lying along the x axis, and then it is a px orbital. So if you fix the axis of AB molecule as a z axis, then the atom A and as well as atom B should use the orbital lying along the axis, so that a sigma bond is formed. Then the remaining x and y orbitals, px and py orbitals, cannot be used to form a sigma bond. They have to be used for forming a pi bond. So pi bonds are formed by px or py orbitals, or by both. In some cases both are used, but if we fix the axis of AB molecule as y axis, then the A and B, okay, the atom A should use the orbital lying along this axis to form a sigma bonds. So then other axis, then the other two axis, other two orbital lying along the other axis can be used for forming a pi bonds. So conventionally it is AB axis, internuclear axis is taken as a z axis. So accordingly the this is a pz axis, this is a pz orbital is used to form a sigma bond. Other two orbitals px and py are for forming pi bonds. So pi bonds are formed in general by the parallel overlap of the atomic orbitals, which is in contrast to the sigma bonds. As you can see here, a sigma bond is formed by the head on overlap. These are all head on overlaps in general. Okay, why it is called head on overlap? If you consider the p orbital head, this one has a head which is overlapping with the head of the other orbital, so it is a head on overlap. For p orbital everywhere it is head, because everywhere it is positive, so that's why it is called head on overlap. This type of axial, okay, overlap is very good for forming a bond, and the overlap is more. As a result, the bond formed out of that is stronger and shorter. So okay, so in general sigma bonds are stronger than pi bonds, because pi bonds are formed by parallel overlap. So let us say this is a px orbital combining with another px orbital, then you can have like that. Plus plus minus minus, these are the two atoms. So here this is the internuclear axis. So this is the internuclear axis. Here atom A, here atom B. So they overlap. So as you can see here, pi bond. So this is a pi bond by parallel overlap. So in this case, pi bond is formed by the parallel overlap of the suitable p orbitals. Here it is px, sometimes py. If it is a px, so you can also have a pi bond if you take py orbital. So let us say it is oriented in this way. Okay, so this is plus, this minus, and then there is a p y orbital. Okay, so here they can combine to form a pi bonds of this type. Okay, so this is again a pi bond formed by py orbitals. This is px orbitals. Here the overlap is less, as a result the bond strength is lower compared to a sigma bonds, probably because when they overlap, there will be a interaction, a repulsion between the two nuclei of this. Here there is a nucleus, there is a nucleus, so that they cannot get closer too much, so that the overlap is less compared to a head-on overlap, where there is a direct head-on overlap which leads to a stronger bond. But here it is only a parallel, so that means these two orbitals are parallel to each other, but it is perpendicular to the internuclear axis. So this is a internuclear axis, this is a internuclear axis, this is internuclear axis, and these two orbitals are parallel to each other. So and it is perpendicular to the internuclear axis. So as a result, the then this can be described in this way. So you have a internuclear axis, two atoms are here, and then they form clouds, electron clouds of this type. Okay, so here is a positive, this is a negative. So this internuclear axis contains the two nuclei, and then on top of that, so that forms a plane. There is a plane containing these two atoms. Then above the plane there is some electron cloud, below the plane there is some electron cloud. So these two are called 1 pi bonds. Okay, these are all pi bonds which are represented in this type of long elongated of this shape. Now let us see bonding nature in ethenes or ethylene. Now you know that for carbon, if you look at the carbon is linked to 3 atoms, 2 hydrogen, 1 carbon atom. So carbon is sp2 hybridized orbitals. Now if you take a electronic configuration of the carbon, this is a 2s orbital containing 2 electron, and then you have a 2p orbital containing 2 electrons. Then it has to undergo sp2 hybridization, sp2 hybridization. Then it has to undergo first promotion of electron to here, and then it has to undergo sp2 hybridization. Then you will have promotion of electron and hybridization. Then that will lead to 3 equivalent sp2 hybrid orbitals containing 1 electron each, and there is one more p orbital which is not hybridized containing 1 electrons. Okay. This orbital can be px or py orbital. So electron is promoted to this level, and then it undergoes hybridization to give 3 sp2 hybridized orbital containing 1 electron, and they are equal in energy, and there is one more orbital which is not hybridized, which lies there, which is higher in energy, which lies there, that is a pure p orbital. It can be a pure p orbital, one of the p orbital, px or py orbital. Now carbon could use these 3 sp2 hybridized orbital to form 3 bonds. Okay, so you have a carbon. So when it is sp2 hybridization, it is a trigonal planar geometry. So you have a trigonal planar geometry. This is sp2 hybridized orbital, and then each one, 2 of them forms a sigma bond with hydrogen 1s orbital. Hydrogen 1s orbital, a sigma bond is formed between carbon and hydrogen. This is hydrogen, this is hydrogen, and then another sp2 hybridized orbital is used to form a sigma bond with another adjacent these CH2 groups, which also contain sp2 hybridized orbitals, sp2 hybridized orbital. So this is a sigma bond by sp2 overlap. Here sp2 hydrogen 1s orbital, here again sp2 hydrogen 1s orbital. So this is how it is carbon, here carbon, and then you have hydrogen, and we have hydrogen, and you have hydrogen. Okay. But so what we have seen so far is the formation of sigma bonds, but if you look in the structure there is another bond, okay, because carbon has a 4 valence, only 3 are written, one more valence is not satisfied. So you have to, you know that there is a p orbital lying on each carbon atom. So there is a p orbital here, there is a p orbital here, it can, which can be px or px or py orbital, which can overlap with the same px py orbital lying on the other adjacent carbon atom. Okay. So they can interact and they can interact. Okay. Then there is a pi bond formation. This is pi bond. Okay. That pi bond is above the plane formed by the 4 these carbon, okay, CH2 sigma bonded CH2. So these 2 hydrogen and carbon and this carbon 2 hydrogen are in a plane. Above that plane there is a cloud of electrons and below the plane there is a cloud of electron. That clouds of electrons is called pi bonds. A pi bond is formed by the overlap of the px or py orbital of the one carbon atom with the px py orbital of the another carbon atom, and it also contains sigma bond. So in ethylene okay, there is a one sigma bond and there is one pi bond between 2 carbon atoms. So let us see the bonding nature in ethynes or acetyl or acetylene. That is hydrogen C triple bond carbon hydrogen. Now you can see that the carbon is linked to 2 atoms. Here is one atom, here is another atom. So it is sp hybridizer orbitals, and there is no lone pair on the carbon atom. So it is all sigma bond. Okay, it is all bonded. There is no lone pairs. So it is sp hybridized orbital. That means sp hybridization means diagonal hybrid orbitals. So carbon has 2s orbital containing 2 electrons, 2s orbital, and there is a 2p orbital like that. Then it has to undergo promotion of electron and hybridization, hybridize. Then okay, then you will have hybridized orbital, 2 hybridized orbitals, okay, containing 1 electrons here and here, and then there are 2 more unhybridized orbital containing 1 electrons like that. Okay. So number of valence electron is 4. Here is a 4, here also 4. After hybridization, promotion of electron, hybridization, number of valence electron is not changed, it remains the same, but okay, the energy levels are changed. So 2 of them, okay, yeah, 2 of the sp hybridized orbital. This is sp hybridized orbitals, sp hybrid orbital. Here is the pure p orbital. It can be px and py orbitals, which are not hybridized. Now, so you have a carbon containing okay, sp hybridized orbital, which are pointed in opposite directions. So you have carbon here. Similarly, you have another carbon here, okay, which also contains same type of sp hybridized orbital that can overlap with this carbon sp orbital, okay, and then this orbital can overlap with the hydrogen 1s orbital. Okay. Similarly, this sp orbital can overlap with the hydrogen 1s orbital. So this is sp hybridized. So this is sp, this is again sp. So sp, this hydrogen 1s orbital. So which is equal to hydrogen carbon sigma bonded carbon and then hydrogen. And then you know that there is a there are two more pure p orbitals are there on each carbon atoms. So there is a p orbital lying along the x axis, and then there is another py orbital lying along the y axis. So it is a py orbital, this is px orbital. So this is a plus minus, this is my plus, this minus. Similarly you have a p here px orbital and then py orbital, and then so there can be overlap between this px orbital and then between and then here is a positive. So here and then there is a overlap between py and py orbitals. Okay, so that will give two pi bonds, carbon a sigma bond and then hydrogen here and hydrogen here, and there is a two pi bonds which are perpendicular to each other. So if you say this is a positive negative, then this is negative, this is positive. So because px and py orbitals are orthogonal to each other, the pi bonds formed by them are also orthogonal to each other. They are perpendicular to each other, or perpendicular to the internuclear axis. So ethane or acetylene contains two types of bonds between two carbon atom. One is the a sigma bond, and then there are two pi bonds, Okay. So so far we have seen hybridization of orbitals. What are those orbitals? Between hybridization between s and p orbital. It's also possible to have hybridization between sp and d orbitals. Okay, you have s orbital, p orbital, and then d orbital you have f orbital. We are not going to see this one. Okay, because that is higher in energy, but d orbital is accessible by energy. So if you go to third row elements, for example phosphorus or sulfur, these are third row main group elements, they have accessible d orbitals. So it is possible, if you look at the energy levels of the d orbital present in phosphorus and sulfur, okay, compared to energy levels of s and p orbital, they are comparable. So it is like that. So if you take a phosphorus atom, you have a 3s orbital. First is the 3s orbital, you have 3s orbital and then 3p orbital. On top of that there is a 3d orbitals. Then above that 4s orbital is there, and then 4p orbital is there. Now these energy levels are comparable. Okay. So if you say this is the energy level of the 3d orbital, and then okay, so it's 3p, okay, 3p orbital energy level is there, then 3s orbital is like that, right? And then on top of that you have 4s orbital, and then on top of that 4p orbitals. So energy level of the 3d orbital is comparable with the energy levels of s and p orbitals. Similarly, it is comparable with 4s and 4p orbitals. As a result, there is a possibility for hybridization of 3s 3p orbital with 3d orbital, as well as hybridization of 4s 4p orbital with 3d orbitals. So you can have sp3 d using this. So using this one, sp3 d as well as sp3 d2. Similarly, it is also possible here, it's a d2 sp3 hybridizations are possible. Let us see some examples now. sp3 d hybridization possible, and then because there are 5 hybridized orbitals, here 4, another one is a 5. If it is a 5 hybridized orbital, the geometry is a trigonal bipyramidal. Tetrahedral pi pyramidal. The examples are PF5, PCl5. You can also have hybridization Sp3D2. The geometry is a square pyramidal. Okay. Square pyramidal, you know the shape of that. This is a square pyramidal. Okay. There is no bond between this. For example, this is a for example bromine. Bromine square pyramidal. Okay. And then there is a lone pair here. Okay. So this is a BrF5. Here is a fluorine, here is a fluorine, here is a fluorine, here is a fluorine, and there is no bond between two fluorine atoms. But to show the shape of the square pyramidal, I drawn a line between each pairs, and there is a lone pair here. Okay. So but there is a bond here, and here there is a bond, there is a bond, and there is a bond. So the shape of the molecule is a square pyramidal. Another molecule, another hybridization is the Sp3D2. Here so there are 4 orbital, another 2 more, so 6 orbitals are there, hybridized orbitals. So geometry is octahedral. Examples are SF6, CrF6 3-. You can also have D2 Sp3 hybridization. For them, its geometry is octahedral. Examples are CO ammonia hexamine 3+, like that. You can also have DS Sp2. So 1 d orbital hybridized with 1 s orbital and 2 p orbitals. So geometry is a square planar. Examples are transition metal complexes. Now we are not going to discuss about structure of transition metal complexes, platinum, nickel, cobalt. We are going to see only the structure of main group compounds. Let us see the structure of PCl5 or PCl5, for example, or PF5, PCl5. Okay. So if you look at the electronic configuration, the phosphorus atom, the valence orbital is the 3s orbital containing 2 electrons. On top of that, you have a 3p orbital of this. There is a 1 electron everywhere, and there is a empty d orbital. Okay, 1, 2, 3, 4, 5. There are 5 d orbitals. So this is 3d orbital. This is 3p orbital. Now, to form a 5 bonds, you have only 3 p orbitals containing 1 electron each. So there must be 2 more hybridized orbital or orbitals available with phosphorus, so that it can form 5 bonds. So so the process is promotion of electron from 3s orbital to the 3d orbital. So promotion of electron gives energy level of this type. This is 3s orbital contain 1 electron, because one of the electron is gone to 3d orbital, that I will show you now here. And then there is a 1, 2, 3, 4, 5, 3, 5. So here it's gone. Now you can see that electron is promoted from 3s orbital to 3d orbital. Now these orbitals, after promotion, orbitals should undergo hybridization. Hybridize and giving 5 equivalent hybridized orbitals. One, two, three, four, 3, 4. So you can have 1, 2, 3, 4, 5, and then there is a okay. So it is a Sp3 3d hybridized orbital, and there are unhybridized d orbital, remaining is 4 d orbitals, because one of the d orbital is used for hybridization with sp orbitals. This is a 3p orbital, this is 3d orbitals. So, okay, so hybridization between 3s, 3p and 3d, one of the orbital is used. We will see which is that orbital. So, after that you have sp3d hybridized orbital, 5 sp3, there are 5 sp3 hybridized orbital which are equivalent energy, which are not equivalent energy, and I will show you. Unlike carbon, you have sp3 hybridized orbital. Here there are two types of hybridized orbitals. Here is the empty d orbitals. So, the geometry for the PCl5 is the trigonal bipyramidal geometry. So, the phosphorus, you have phosphorus, and then you have here sp3d hybridized orbitals like this, and then you can bring the chlorine towards the phosphorus atom, which is having a sp3d hybridized orbital ready for forming bond. So, you have a head-on overlap between the chlorine singly filled p orbitals. So, that is a positive, this is a negative. Okay, so this is a chlorine, and then similarly you can have a overlap with another chlorine atom. You can also have a overlap with p orbital of the another chlorine atom. These are the chlorine atom p orbitals. Okay, so you have, there is a p orbital chlorine atom, and then you have okay, chlorine atom p orbitals. So, 5 sigma bonds are, this is equal to p, c, cl, 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 cl. So, trigonal bipyramidal. So, here in this molecule there are two types of bonds. Okay. So, this is a plane. Okay. So, this plane is called equatorial plane. Equatorial plane. The orbitals used to form form bonds with these 3 chlorine atoms is called equatorial orbitals. So, these bonds are also called equatorial bonds. Okay, and these two are axial bonds. These two are axial bonds. Okay, these 3, 1, 2, 3, these are called equatorial bonds. Equatorial bonds. They are different. Now, which is orbitals used for which, for forming which type of bonds? So, you have here okay, so carbon, the phosphorus has a, okay, there are 3 p orbitals. So, let us say this is x orbital, px orbital, this is py orbital, pz orbital, and then 3s orbital, and then here. So, to form a axial bond, phosphorus uses its pz orbital, pz orbital, and okay, dz square orbital for forming axial bonds. Okay, because they are oriented, these two orbitals are oriented along the z axis. Okay, so along the z axis, which are used to form axial bond. Then the remaining orbitals are s orbital, and then px and py orbital for forming equatorial bonds. Equatorial bonds are used. So, it becomes clear that there are two sets of hybridized orbitals. One set is the pz and dz square orbital, which are used for forming axial bond. These are the axial bonds also. So, which is okay, that is slightly different in energy compared to the energy of the 3 equatorial bonds. These are the equatorial 1, 2, 3. These are the equatorial bonds formed by another set of hybridized orbital, which is s, px, py hybridized orbitals. As a result, they are different in terms of bond energy, in other words bond strength. So, actually sp2 hybridized orbitals are good for forming stronger bonds. So, they are shorter compared to pz, dz square orbitals, they are longer. So, these bonds, the axial bonds are longer, relatively little bit longer. Okay. These bonds are shorter, okay, because the overlap of the sp2 hybridized orbital with carbon or with chlorine p orbital is greater compared to the overlap formed between chlorine p orbital and pz and dz square orbitals. This can also be explained as a result. These two bonds are longer compared to the phosphorus chlorine bond of the equatorial bonds. So, this could also be the difference in bond length or bond strength could also be explained by invoking the repulsion between the bonding electron pairs. So, this chlorine atom is repelled by, okay, or this bonding electron is repelled by 3 bonding electron present in the equatorial plane. So, one bonding pair, there is another bonding pair, there is another bonding, all of them repel the bonding pair between this chlorine atom and phosphorus atom. So, as a result they get away from each other. So, the bond length is increase, for axial bonds. Yes, F6. Here again 3s orbital, you have 3s orbital containing 2 electron, and then you have 3p orbital, okay, like this, okay, the same what is that called, doubly filled orbital. On top of that you have a d orbital, okay, which is empty, 3d orbital. So, promotion of electron followed by hybridization gives 6 equivalent sp3 d2 orbitals. 1, 2, 3, 4, 5. So, 1 electron here, 1, 3, 4, 5, 6, and then you are left with 3 unused unhybridized 3d orbitals, which is empty. Here this one is the sp3 and then d2, okay. So, 1 s orbital and then 3 p orbital. So, sp3 and then 2 d orbitals were used. So, you have d2. So, sp3 d2 hybridized orbitals. Which are ready for forming a bond with fluorines. The structure is like that. You have a middle sulfur and then arrange the, so because there are 6 orbitals are there, the expected geometry is octahedral. You can draw the structure like this, okay. So, these are the lobes of the sp3 d2 hybridized orbital, which are projected towards the corners of the octahedron geometry. So, okay, so here this orbital could overlap with the p orbital of the fluorines. This is fluorine p orbital, which is singly filled, p orbital of the fluorine. Fluorine, fluorine, fluorine. So, this is equal to sulfur like that. So, octahedral geometry, it has a octahedral geometry. So, sigma bonds or bonds are formed by overlap of the atomic orbitals. So, let me summarize them. If you have sp hybridized orbital, sp hybridization, the expected geometry is linear. The geometry is linear. Then that means it has 2 sigma bonds. The angle are 180. If you have sp2 hybridization, the geometry is a trigonal planar geometry. Trigonal planar, which contains 3 sigma bonds. Okay. It can also give bent geometry, but it has only 2 sigma bonds. Okay. because there is a another okay, there is a another okay, another sp2 hybridized orbital is occupied by a lone pairs. So you have only 2 sigma bonds. Okay, so you have a middle atom and then there are 2 like water. So it is a bent structure, you have only 2 sigma bonds. Okay, if there is a 3 sigma bonds, it is a trigonal planar. If it is only 2 sigma bonds, then it is a bend for sp2 hybridization. Now let us see sp3. If it is you can you are familiar with the tetrahedral geometry, which contains 4 sigma bonds. It can also have trigonal pyramidal. And it contains 3 sigma bonds, okay, only 3 sigma bonds, and then it can also be a bend geometry. It has 2 sigma bonds. So the angles are here 109.5. In case of sp2 hybridization, the angle is 120 degree. So if you have sp3 hybridization, the familiar geometry is a tetrahedral. That means there is a 4 sigma bonds. Okay, it can also give trigonal pyramidal. That means only it has 3 sigma bonds, because there is because one of the sp3 hybridized orbital is occupied by lone pair. Similarly, 2 of the sp3 hybridized orbital occupied by 2 lone pairs, then you are left with only 2 sigma bonds. Then in that case the geometry is bent. Okay, so then you have sp3d hybridization, then you have a trigonal pyramidal geometry. Pyramidal, that means it has a 5 sigma bonds. Okay, so 5 sigma bonds. Then you can also have seesaw structure, then it has only 4 sigma bonds. It has only 4 sigma bonds. You can also have T-shape geometry. In that case only 3 sigma bonds are there, because there are 2 lone pairs are there. It has only one lone pair, it has 2 lone pairs, but it contains 3 sigma bonds. So the geometry is a T shape. It can also be linear. So in that case only 2 sigma bonds, only 2 sigma bonds are there. Remaining are for lone pairs. The angles are here 90 degree, 120 degree, and then 180 degree. Thank you.